learning model.
Hi, I'm Jian. Today I'm going to talk about the reinforcement learning and how it can be married to fMRI. As just Brandon briefly mentioned, he sort of gave the leak to my presentation already. Recently, reinforcement learning has really enjoyed a surge in terms of its popularity. And I think one of the major reasons is because the recent rise of AI and machine learning. Just click. Yeah. You know, we live in a sort of rather uncertain world. If everything is quite certain to us, then making decisions is very easy, right? Just pick up the ones that give us the most reward. But we know things are quite complicated. For example, in this case, which direction you should go, really, you have some clues, but the clues are not exact, and you can't just blindly follow the clues to get to where you want. One of the principles to solve this problem is using reinforcement learning. And today I'm going to talk about how reinforcement learning can be combined with the computations in the brain. And one of the classic papers making these suggestions is a paper talking about the dopaminergic systems in the brain. So there are some dopaminergic neurons in the brain that project to different brain areas. And one of the classic work in the 1990s showed that those dopaminergic neurons, instead of just signaling reward, it signals something different. This is a paper now. It's a very classic paper. As you can see that from the very beginning, if a monkey gets some type of reward unexpectedly, the midbrain dopaminergic neurons sort of fired. And later on, when this training, there's a CS, a neutral cue is paired with the reward for extended period of time, the dopaminergic neurons firing patterns shifted to the onset of the CS, but when the reward was delivered, nothing happened to those neurons' activity. Later on, the funny thing is that when the CS was up, but by the time the reward was supposed to be given, but no reward was delivered, you see this decrease of dopaminergic activities. For quite a while, this has been a puzzle in both sort of learning literature and neurophysiological field. Eventually, people come up with this idea that those dopaminergic neurons actually were signaling, instead of reward itself, it was signaling reward prediction errors. And briefly, or simply put, you can define the prediction errors as what you get minus what you expect. If you follow this kind of definition, now the mysterious patterns of dopaminergic neurons is not mysterious anymore. For example, in this case, in the early trials, you didn't expect anything, but you do get a drop of juice or water, and that's why it gives you a positive dopaminergic response. When the training happened for a long time, now you expect something, and you did get something, so the response gets cancelled out. That's why the reward delivery didn't cause any dopaminergic firings. Same thing happened later. When you expect reward, but you didn't get anything, that's why you have a sort of a negative, which is reflected here by the pause of the neural firings of those dopaminergic neurons. Of course, this is very sort of simple and schematic representation of the dopaminergic neurons. Now we are trying to come up with sort of more dynamic ways of looking at the neuronal patterns that's linked to the dopaminergic pathway, and also how the theoretical foundations of reinforcement learning. Really, depending on how you look at the question, you can slice the reinforcement learning theories into sort of different categories. If you focus on the value iteration process, basically you can divide the reinforcement learning into the very popular temporal difference learning and also the Q learning. Some of you might be very familiar. The actor-critic, which the prediction error signal can train the actor and critic. That's for the model-free part, and also you have this model-based part, which Brandon just mentioned. I will talk about that later. If you just use the policy iteration, basically the idea is that instead of generating value signals for different options, now you internally represent a policy telling you which option to choose, and then use the prediction errors to directly interrogate this policy, tell you next trial whether you should move away or towards certain action. Okay. Of course, you can get even more complicated by, for example, the hierarchical reinforcement learning, and also this multidimensional reinforcement learning. Those are the classic papers that you might want to refer to if you're interested. Today, for the sake of time and also the sort of popularity, I'm going to talk about there's three types of reinforcement learnings: the TD and Q learning, and also the model-based ones. Since this is a sort of educational talk, I'm going to briefly mention how, once we have picked a model, how we're going to do with this model. We know we usually perform experiments. We collect some data. The data can be either behavior, choice, reaction time, or physiological. For example, skin conductance, heart rate. Once we have those data on hand and we pick the model, we can do model fitting. And model fitting, in general, there are two approaches. One is called point estimation. In the sort of linear regression field, we already know the least square errors, and it can also be used in more complicated model fittings. But most commonly used methods in point estimation is probably the maximum likelihood estimation. Okay, and but the drawback of maximum likelihood estimation is that sometimes when people's behavior, especially individual behavior, there's a lot of variance in it, the maximum likelihood estimation tends to give people pretty absurd parameters. In order to adjust that question, you can try this maximum a posteriori method. Basically, this method is by imposing a prior distribution on the parameters, so that now if you combine or time the prior distribution with the likelihood to generate the posterior distribution of certain probability of certain parameters, you have a nicely constrained parameter space posteriori. If the models also involve some latent variables, you may also want to try expectation maximization for point estimation. This, for example, is very useful in Gaussian mixture models. Recently, there's a trend, especially for the Bayesian lovers. They tend to do this posterior distribution approximations. Out of those, you have Monte Carlo Markov chain, the Metropolis-Hastings method or Gibbs sampling, and then you have this particle filter. Also, if you want to make the model even more complicated, you can do this hierarchical Bayesian estimation. The idea is that for the individual parameters you have on your hand, you assume there's a group sort of distribution of the parameters which governs each individual parameter. For the model comparison, usually this comes when we have sort of different candidate models at hand, and then the problem becomes which model is the best in terms of explaining or for your behavior data. There's some methods that people are commonly using, for example, the AIC criteria, the Akiki information criteria, or the BIC, the Bayesian information criteria. That's for, and also you can do the Bayesian model comparisons. I'm just laying out all the possible sort of methods that you can possibly use if you are interested in this type of model comparisons. Of course, these are not specifically restricted to reinforcement learning modeling process. It's for any sort of behavior modeling. Eventually, once you pick the RL model, once you have this model fitting to your data and generated regressors of interest, for example, in reinforcement learning, typically people generate regressors such as prediction errors and expected values for certain options. And also, for another one of interest might be the vigilance signal. how people sort of are sensitive towards prediction errors for each trial. Once you have those parameters or trial-by-trial variables, what happened is that you extract those trial-by-trial variable and you convolve them with a standard hemodynamic response function to generate a predicted hemodynamic response. And then you go to the brain and search all the hundreds of thousands of voxels and trying to find which voxel gives you the neuronal pattern that looks very similar to the pattern that you just predicted. Okay? Okay, now we're going to talk about, this is just sort of toy examples of 3 different reinforcement learning algorithms. The first one is the temporal difference one. In the temporal difference learning, there are states. You can think of them, the states, as sort of different time points in your trial. In each state, there's a value associated to it. The optimum value or the real value for that state is the discounted values starting from that state to the future until the trial ends or the session ends. Of course, before the experiment starts, nobody knows exactly what the state value is. That's where the temporal difference comes from. Suppose you're starting from this state. Now you start moving to the next state, but on the way there, you received a certain amount of reward. If the reward is accurate, that means your prediction starting from this state is completely equal to what you are going to receive, and starting from the next state, the value of that state. If this is accurate, of course, there's no prediction error. You don't have to do anything. But if the prediction is not accurate, the current estimation of the state value doesn't match what you received from that state on, then you generate a prediction error. Once you have that prediction error, you can calculate the amount of prediction error and use that, going back to update, now the new value of that specific state. Okay? And by doing these iterations, you can fit this model to, for example, people's choice or physiological response data. Probably the sort of the simplest version of the TD model is the delta rule that people are very familiar with. In psychology, people used to call them the Raskiller-Wagner model. The idea is that you have expectation, the new expectation equals the old expectation plus prediction error times a constant learning rate. Okay, you can rewrite this equation as the new expectation of certain stimuli or Q equals to a linear a combination of the previous value expectation plus the reward you just received. Okay. This is a very sort of classic paper using TD learning in a passive sort of Pavlovian conditioning experiment. The setup is very simple. You have different Qs, but it's secondary conditioning. You start from QA, and most of the chance the QA will lead to QB, and then QB will deterministically lead to a high level of electric shock. But occasionally QA will lead to QD, and vice versa for QC. You know, QC most of the time goes to QD, and QD leads to a low electric shock. But sometimes QC goes to QB. Okay. If you ask human subjects to do this, they learn this task very fast. Based on the paradigm, something that we can do is to generate 2 types of regressors. One is the so-called the temporal difference value regressor. That is, when the Q comes up, what do you expect? For example, for this first one, the QA comes up. Since QA most of the time leads to QB and then to the high electric shock, so when QA comes up, you know quite sure that you're going to receive a shock. Okay? Suppose that learning already completed. But for QC, which is this guy, you know, once QC shows up, most likely you're not going to get anything. But until QC is switched to QB, now you know that you're going to receive a big shock. Okay? So by fitting the learning models into people's behavior, in this case skin conductive skin conductance data, you can generate this type of regressors. This is for the value, state value representation, and these regressors are for the prediction error regressors. And the next thing you can do is just, I mentioned earlier, you can convolve those sort of time series regressors with a canonical hemodynamic response function and go to the brain and look for the neuronal sort of correlates for those regressors. And not surprisingly, as Brenda mentioned, usually if you use the prediction error and you go into the brain, what you find is typically like midbrain or striatum. Of course, you can make the model even more complicated because before we were assuming that the learning rate is constant. Now you can even make a sort of hybrid model by change the learning rate to a dynamic variable. Now you have both the prediction error as sort of a variable, and then the learning rate as another dynamic variables. And then same thing happens. You go to the brain and look for the learning rate, which now is not a constant parameter for each subject. It varies with trials, and also the prediction error. By fitting the model to people's skin conductance, you can see, usually they get a reasonable fit. And then you go to the brain, you find, prediction error seems to be located in the ventral striatum, and the dynamic learning rate seems to be associated with activities in the human amygdala. Okay, now really quickly jump to the Q-learning part. And the Q-learning basically solves the question of when you have, you still have states in this kind of games, but now you have control. Basically, you can make a decision as to which way to go. For example, in the maze running task, if you're mice, you're standing at the starting point, you can go right. Once you reach state 2, you can decide to go to state 3 or go back to state 1, which is the starting point. This is sort of typical dilemma that a robot is facing. In this case, the robot is really moving in this terrain. Of course, if the robot touches the bomb, then game ends. If it touches the lightning signal, it will collect a certain amount of reward. The final goal is to train the robot so that the robot learns which way or which is the most efficient way to get to the end point. Typically, for this type of experiment or paradigms, we use Q-learnings. The Q-learning is nothing but adding sort of one more dimensions to the temporal difference learning algorithms. In temporal difference learning, the time just the passively goes by. But in Q-learnings, you have a decision to make. You can go either right or down for each option. And the updating rule is that once you, for example, we can assign sort of default values for all these states, and then once you visit a new state, you get to collect what's in that state. For example, you go from here to here, you collect one sort of unit of reward, but also you get to update how good this current state is. That's the idea. And this is sort of the pseudocode for the updating algorithms. Here is just a sort of dummy examples. Suppose that you are in room 2 and your final goal is to get out of the room, which is defined by, denoted by number 5 here. Starting from the very beginning, the state here 10125 labels the names or the numbers of different rooms. You can take different actions. For example, if you're in room number 1, just by going to number 5, you exit the room, and then you can artificially assign a big sort of number of reward that encourages people to go from room number 1 to outside. Following the same mechanism we just talked about, you can easily see how this sort of Q-learning model works. For example, if you're starting from state number 1, which is here, if you go out, if you just happen to make a decision to go out, and then you collected a big amount of reward, how big is that? So this is sort of Q-learning tables, right? If you're starting from state 1, you go to 5, you collect 100. And this equation tells you how to update that. The new sort of Q value for that state 1 and 5, at state 1, take action 5 equals to the old value, which is 0. and plus some sort of learning rate times the maximum amount of if you're standing at state 5 and what you're going to do, right? So this will give you updating algorithms. Now the Q value sort of lookup table, instead of all zeros, this is the sort of initial setup. Now you updated the Q value lookup table. Now you know from state 1, room 1, if you take action 5, which is going out, you're going to be collecting 100 unit of reward. You can do this kind of iterations all continuously until you sort of converge the Q lookup table into some stable values. In this case, you realize that no matter where you start, for example, in this case, you're starting from room 2, you know going to room 3 will give you, the Q value of going to room 3 will give you 64 unit of reward. And starting from room 3, which is here, you can either go to room 4 and exit from there, or you can go to room 1 and exit from there. Once you train this Q value lookup table well, and then you can follow this trajectory very easy. Pick any state you're at and just look at all the values associated with different actions and pick the ones that give you the biggest state action value. Of course, this prediction error signal can be used, as we mentioned, to update the state values. That's something we did. And also can be used to update action selection, which is sort of policy interrogation, which we will not talk about. The last one, sort of, or the last to the second, this is a simple sort of one-stage experiment. You have two options, which people usually do in their experiment. You press those two options. Every time you select either one on the left, on the right, you receive certain amount of reward, which is represented by the bar height in the middle. You keep doing this until you find, which option is the best one. And typically, solving this type of problems involves Q-learning, right? You assign Q values for each option, and then you update those Q values based on the reward you received. For example, you press this option, you get certain amount of reward, and use that to interrogate or to subtract the previous expectation to generate the prediction error signal, and use that error signal to update your value expectations for both option A and option B. Once you have a fairly or rather accurate representations of the state or action values, and then you can feed them into action generation process. Again, if you do that, you pull out the venture stratum, as people usually do. Lastly, I'm going to talk about the now very popular ideas of the model-based or model-free reinforcement learning. This idea actually is rather straightforward. This idea all comes from this original paper in 2010 by Nathaniel et al. It captures this intuition. So, for example, this is a two-stage decision-making or learning problem. At the early stage, or stage 1, you have two cues on the screen. By choosing one of the cues, and that cue will lead you to another two states. Most of the time, it will lead to a state in the green state. 30% of the time, if you choose that cue on the left, it will lead you to another state, the blue state. The vice versa for the option on the right side of the screen. The interesting is this. So once, for example, if you choose this option and landed you here, you and then choose one of the options following that, you received a certain amount of reward, or you didn't receive an amount of reward. The question is about how do you assign credit. If you choose this option and you do receive reward, of course, this guy tells you, this is a better option. Next time, I might be more inclined to choose this option. But the interesting thing is not about this; it's about these two. So, model-free reinforcement learning will give you an intuition that, given you choose this one and lead you there, that means if this turns out to be good, then this guy is good, but also this guy is good, right? Because it tells you to go there and you collect a certain amount of reward. But model-based RL will give you a different prediction. This may be more clearly demonstrated here. For example, in the model, the model-free mechanism basically tells you in a rare condition, the red one, if you in a rare condition, for example, you choose this option, most of the time it goes here, but in a rare condition it goes here. In this condition, if you receive certain amount of reward, so you know this action must be good, but then preceding this action is this one, so this one must be good, right? But we know from a model-based perspective, most of the time this option doesn't lead you here, it's this option. So there is a direct contradiction between the predictions of the model-free reinforcement learning and the model-based ones. If you just focus on the red bar in the rare condition and also that red bar in the of the rare condition in the unrewarded situations. So to capture this intuition, people developed this model-based, model-free approach. In the model-free, just as I described earlier, it's just a simple Q-learning. But in this case, remember, in order for you to get to assign credit to the sort of the second order or the higher order of the actions, you need to add an eligibility trace. But that's something else that we can talk about. In the model-based approach, things can be quite different. In this case, you assume people already know the state transition matrix. For example, in this case, somehow people already have a map in their mind. They know that by choosing the options on the left, they have 70% of chance going here and 30% chance going there. Same thing for the other stimuli, which is quite demanding for the subjects. In order to calculate the state action values, the subjects or the animals need to do all these calculations online whenever they see a stimulus comes on. That requires a lot of sort of working memory loads. Once you have the model-free and model-based components, what these people did is that they constructed a hybrid model by linearly combining the model-based component and also model-free component and generate a net Q value for each state action pairs. And again, they feed these pairs into this policy algorithms to generate or predict certain actions based on which state or which actions the subject is taking. So that's for the model-based, model-free approach. So, and if you use the prediction errors generated from the model-free approach as well as from the model-based approach, because those two prediction errors, they're sort of uncorrelated with each other. And then if you use them to go to the brain and hunt for their neural correlates, and surprisingly, you find neural activities in the striatum that correlates with both type of prediction errors. This tends to suggest that the processing of both type of prediction errors seems to be sort of co-localized in the same brain areas, meaning that this brain structure is responsible for two types of reinforcement learning mechanisms. So just to wrap up, I hope I have time or have the clarity to tell you about all these three different learning mechanisms using examples. The temporal difference learning using now the classic papers of the secondary conditioning paper of 2003, and then the Q-learning using the robot example. And if you're interested in the model-based, model-free approach, you should go and read this paper, which is also classic in the 210. Okay, thank you.